Um, okay, so in the last class we discussed, I mean, in the last few classes we are discussing about the current flow in a PN junction through a PN junction. So we talked about uh, two injection condition. One is low level injection condition. We started with low level injection. For the low level injection, the condition was the holes that were injecting is less than ND. Let's say because I'm forward biasing the PN junction, I'm injecting holes from P to N. I'm injecting electrons from N to P. So delta PN is how much holes are injected from P to N. At the edge of the depletion region at x equal to xn, this is less than ND, right? So this is my low level conditions for low level injection, and delta NP is similarly as I've discussed just earlier, is less than Na, right? And we derived taking this means different conditions, means we derived that your current, total current, which is the summation of electron current as well as hole current, is nothing but Q times Ni square divided into dn by NaLn plus dp by ndlp times e to the cube v of kt minus 1, right? So this is my current equation. So in the reverse bias condition, right, so we applied is uh, because in the reverse bias condition your this term, right, uh, e to the power q v applied by kt will be less than 1, right? So so in the reverse bias condition, then your current will be just q times ni square into dn by nln plus dp by ndlp, right? So this is my reverse saturation current. So we call it J0 because this current is constant. So we call it reverse saturation current, right? Okay. So then if I do means this is for a NP junction, but for a N plus P plus N diode, right? So because we are mostly dealing with most of the diode will come across, right, in devices either N plus P or P plus N, right? So for a P plus N diode, where Na is more than Nd, right? Because P plus and N, so Na is much higher than Nd. So there the current is only because of holes, right? So in for a P plus N diode, the current is only because of holes. So my equation, I could write it like this because I just want to, I'll just neglect the electron current, right? So this component here, right, Nd, see my Na is very high. So this part here, right, this part will be neglected, right? Right. So so my total current will be whole current. So J, I can write like this. And then the reverse bias, if I put, I mean, in the reverse bias condition, so it will be Q Ni square dP by NDLP, right? So this is under reverse bias condition, right? Okay. So similarly, for a N plus diode, N plus P diode, my ND is greater than Na. I could also write like this. Your current is because of electron current, right? So N plus P diode is current is because of electrons, right? And the electron current depends on Na, right? So this is a very important thing, right? Your current is because of electrons, but it depends on the doping of the p side, right? So so this is my current for N plus P diode, and similarly I could also write down the reverse bias current will be Q Ni square dn by NaLn, right? So here, if you see the reverse saturation current, right? Reverse saturation current definitely depends on doping Na and also depend on Ni. So reverse saturation current is strongly dependent on Ni, right? Higher the intrinsic carrier concentration, like let's say germanium. Germanium has very high intrinsic carrier concentration because of low band gap. So the reverse saturation current in germanium is much higher than silicon, right? So that you have to keep in mind. Higher the band gap, Ni will be lower, your reverse saturation current will be lower, right? Okay. So now if I plot uh, uh, the IV characteristic of a diode, right? So I think in the lab you will do in the microtronics lab you will do some measurement, PN junction measurement. So for a Okay, for a diode, if I plot current as a function of applied voltage, in the log plot, right? So I'll have a straight line because your current is exponential depends on V applied voltage, right? So your current is exponential dependent on applied voltage. So it will be a straight line, right? Similarly, if you do it in a linear, in the log it will be a straight line, right? If you're only talking about low level injection condition, right? If you're talking only about low level injection condition, which is in the ideal condition, right? So high level injection condition will come when applied voltage is much higher, right? So let's not go to that part. The low level injection part, so your current is linearly dependent, means exponentially dependent on applied voltage. So in the log plot, it will be linear, right? Log is means my current axis is log, my applied voltage axis is still linear, right? Similarly, in the linear plot, if both axes are linear, then my current will be like this. This is exponential dependency, right? So your current will be low, then it rises, right? So if this is for silicon, let's say this is for silicon. If I want to do the same thing for germanium case, because if you see the current equation, so nothing will change. Let's say I have a germanium diode and p side n side is equivalently doped, right? The only thing changing here is Ni, right? So your germanium, I'll have high current, right? So basically, if you see, I'll have high current, right? So this is for germanium, right? So germanium, it will be like this. And if I do for gallium arsenide, which has a higher band gap than silicon, then my current will be like this, right? I could draw it a straight line, right? Yeah. So this is gallium arsenide, right? So, right. So basically, and if you plot in the linear, right? So linear axis also you'll have something like this, right? So um, for a germanium, so this is for germanium, and for gallium arsenide it will be um, right. This is for gallium arsenide, right? Right. So so in basically you see, for germanium, for the same applied voltage you will have higher current because of lower band gap, higher Ni, right? Nothing else, right? So and for gallium arsenide you will have low current at the same voltage, right? If I take the same voltage condition, same bias condition, same applied voltage, so your germanium, your gallium arsenide has this much current, your silicon diode will give you this much current, and but germanium diode will give you more current, right? So this is right, and this is only because of higher intrinsic carrier concentration, right? So uh, so and also in linear characteristic it will, I mean, actually linear characteristics look like that. After some point, current rapidly increases, right? And in the books, it is called the Cotton voltage, or means the turn-on voltage of the diode. So basically, germanium has a very low turn-on voltage, but actually, this is around zero point 0.3 volt here, and this is 0.7 volt, and for gallium arsenide, this is around 1.1 volt, right? But the point is, uh, this voltage are not properly defined, right? So how do you define a turn-on voltage of turn-on voltage of the diode? So this is actually done if you go to the log axis, and let's say I want to see at what voltage your diodes give 1 microamperes per centimeter square, or microamperes per micrometer square of current. So you if you take the constant current, so let's say if I plot at constant current at a um, constant current point, I could define this is my constant current I0, let's say, or J0, right? Or JC, J constant, right, right. So then I could define my voltage. If I define the voltage required to have this J constant is my turn-on voltage of the diode. In that way, we could also define, right? Okay, so this is the turn-on voltage of germanium, This is my turn-on voltage of silicon, and this is my turn-on voltage of gallium arsenide, right? And definitely the turn-on voltage for germanium will be lower because your current is very high because of higher Ni, right? Okay. Here, similarly, if you go to the reverse side, in the reverse side, your germanium will have higher reverse current, reverse saturation current compared to silicon, and silicon has higher reverse saturation current compared to gallium arsenide. This is mainly because of Ni again, right? The intrinsic carrier concentration. Okay. Any questions here? All right. So if not, so let's briefly discuss about high level injection. And Monica had some questions we clarified at the beginning of the class, but high level injection happens at higher applied voltage. So basically the condition for high level injection is the holes you are injecting to the N side or electrons you are injecting to the P side should be more than Na or more than Nd. So this is at the edge of the junction, right? Right. So delta Pn at x equal to xn should be more than Nd. Delta Np at x equal to minus xp should be equal to Na, right? So we have done this derivation in the last class, and we derived that anyway. So the total current is electron current plus hole current, and I mean this is my equation. The only difference here is uh, means this part also we have a difference in this region here, and we have a q ni square there. Now I have q ni dn by ln plus dp by
Sir,
lp, right? And
sir,
then e to the cube here by 2 kt.
sir, your delta Pn should be greater than ND.
Oh, sorry. Yeah. 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 Thank you, Nissan, for pointing this out. Oh, yeah. Delta Pn should be more than Nd, and delta Np should be less more than Na. Okay. So this is the current equation we have derived, but here the only difference is means if you look at the exponential part, anyway your applied voltage is very high, right? So I have just removed this minus one part, right? Because applied voltage is much higher than Kt by Q. So your e to the power, that part will be much higher than 1, right? So minus 1 I have removed. So uh, this is u sorry, e to the power v q vr by 2 kt, but in the low level injection I have 1 kt, but here you have 2 kt, right? So basically the slope will when you plot in the log plot in high level condition, the slope will be different, right? It will slope will be reduced, right? And also we also discussed, right, in the last class. So since the current flowing is very high in this condition, high level injection condition, the current flowing is very high, and this P and N regions that we are talking about, we are previously neglecting the resistivity of those regions, right? And means basically means those regions had some resistivity, but the point is current was so low that I was not worried about the voltage drop, right, across this P and N region, right? But if high level currents, very high level means high current flows, then there will be a finite drop in the P and N region, and because of this finite drop, if I'm applying applied up voltage across this diode or across this V up, then there will be some drop in the N side, which is Vn. Let's say I have a Vn drop in the N side and I have a Vp drop in the P side. So applied voltage reaching at the junction is nothing but V applied minus Vp minus Vn, right? So you just have to replace this applied voltage equal to V applied minus Vp minus Vn, right? And you could and Vp and Vn are the voltage drops in the P and N region, right? Okay, so now I mean I have drawn the band diagram. Basically, because you need to understand the energy band diagram. So in the low level injection condition here, so the first one is for the low level injection condition, right? Low level injection, right? So I think you understand this, right? So this voltage EFN minus EFP will be my V applied voltage, right? Right. And so I have, see this part here. So because I am injecting holes and holes will recombine, right? So basically this distance here, This is my LP, right? So I'm injecting electrons, sorry, injecting holes from P side to N side. This side is P, right? And this side is N, right? So I'm injecting holes from P side to N side. Then the hole concentration is higher. That's why EFP is close to the your EVP, your valence band. And with distance, as you go from the junction, right, your holes, means holes will recombine. So the minority carrier currents, means minority carrier concentration will reduce, so EFP will again merge with EFN, right, after LP, right. So this distance here is LP, and similarly this distance here is LN in this side, and I have this EFN. There is increase in EFN towards the junction, right? Right, and EFN minus EFP is your applied voltage, right? So this is the energy band diagram in the low level injection condition, right? But in the high level injection condition, this is little bit difficult to understand, but don't worry about it. But the point is that, so now I have, when I'm injecting, so holes are injected this part, right? But the whole concentration, right, the whole concentration is, let's say delta Pn is more than Nd, right? So whole concentration is much more than Nd. So I had some electrons, right? I have a Nd number of electrons, but now there is a momentarily increase in the electron concentration also, right? Because low level injection, your electron concentration in the N side is not changing, right? But here your electron concentration will change because you are injecting the holes which is much higher than the electron concentration, equilibrium electron concentration, right? So there will be a change in the EFP, and also there will be change in EFN, right? Uh, because your electron concentration is also going above Nd, right? And right, so then you will have also a EFN, right? So your EFN will also change, right? And EFP will also change. Similarly, in the P side, your EFN EFP will also change, right? So this thing you have to take care. um, Now, if you have a finite voltage drop, if I go to the high level injection, very high current flowing, and there is a finite voltage drop in the P side and N side, then here also you will see a band bending, because you have a finite voltage drop. That means these regions are not quasi neutral, means there is a potential, there is an electric field, right? So then I'll have band bending at this point here, right? Yeah, right. So you have to consider that bending, right? um, right. So this is how your energy band diagram will change from low level injection condition to high level injection condition, and from high level injection conditions to high level injection condition, plus your voltage drop in the P and N region, right? But keep in mind, when you're operating your PN junction, you never go to the high level injection condition, because high level injection condition is very difficult to manage, because very high current flow, and your junction may not withstand this high current flow, right? Right. Your junction may melt or be damaged, right? So you never operate in high level injection condition, but these are the cases, these are the extreme cases, right? High level injection is extreme case, right? But you could go to little bit high level injection just to see that when you measure the IV characteristic of a PN junction, you will see that there is some saturation, right? So again here, okay, so this is um,
सर
yeah.
सर एक क्वेश्चन है सर, ये मीन्स जब हम डायोड का मीन्स डाटा सेट वगैरह देखते हैं, तो जो वोल्टेज ऑपरेटिंग वोल्टेज होता है, तो क्या वो उसका लो लेवल इंजेक्शन के अकॉर्डिंग ही वोल्टेज उसका ऑपरेटिंग सेट किया रहता है?
Yeah, mostly because these are on the safe limit, right? So they tell that, okay, you don't go above that voltage. If you go above that voltage, then your diode may be damaged, right?
ओके
Right.
ओके
See, some diodes, if they're coming with a current limiting resistor, right? uh, but then it could withstand a little bit more current, right? Or more voltage, applied voltage, right? Right. So to, I mean, you could connect a resistor in series with the diode. So basically, what you're doing is that you're applying applied voltage, then you are dropping some part in that resistor, so that this voltage, see, this voltage should not means basically your current depends on the voltage dropped across the junction, right? So you just, if you could drop that voltage, additional voltage outside the junction, right, by connecting a resistor in series with the diode, right, then you will not have high level injection currents.
Okay, sir.
Yeah. All right. So another thing what we have not discussed is, let me copy this part, and I'm not going to discuss about it in more detail because it's not absolutely. I mean, it's not necessary. I mean, I just tell you. So you see, um, what I was telling is, when you forward bias the junction, your holes um, your holes uh, are injected from P to N, and electrons are injected from N to P, right? So let's say electrons are injected and holes are injected from P to N, right? But keep in mind, these electrons and holes, they are going through the depletion region, right? So it's not like that suddenly, means basically the holes are going from P to N, right? So that holes are traveling through the depletion region, right? Similarly, when the electrons are injected from N to P, they are going through the depletion region, right? So in the depletion region, right? So there is a possibility, because you see you have um, let me draw the band diagram. Let's say quickly, if I draw a band diagram, right? So the holes are going here and electrons are coming in this direction here, right? Right. So there is a possibility that some of the holes will recombine, right? And some of the electrons, right? So holes and electron, sorry, it means basically when I'm talking about holes, holes are always flowing in the valence band, right? So I should not write here, but I could, means it's the same thing, but let me write, I should not make any confusion, right? So holes, because holes and electrons, because holes move in the valence band and electrons move in the conduction band. Okay, so there is a possibility that there is a recombination process, right? So because, and that recombination process, because see, generally, I told you, right, in the silicon is an indirect band gap semiconductor, right? Recombination is not that easy, right? But the recombination in case of indirect band gap semiconductor happens through defects, right? So the moment there is a crystal defect or there are impurities, impurity related defects, then it creates a trap label which is somewhere in between EC and EV, and the electrons and holes can recombine through this trap label, right? So, but when you talk about a junction, but junction in a PN junction, if you see how this is fabricated, right? So you had P layer, then you implant N layer, right? So during this implantation, and there are actually the junction has some damage, right? So what you do, right? When you do implantation, you create a lot of damage, right? Then you anneal the silicon, right? When you anneal, these damages are sealed, right? So you just get rid of those damages, right? But it's not, even if you anneal them, anneal the junction at very high temperature, let's say 1000 to 1100 degrees Celsius, not all of the damages are healed, right? So in the junction, you always have some defects present, right? And if your fabrication process is very bad, right, then you have more number of defects at the junction, right? So so this junction has defects, so there is some recombination mostly happens at the junction region, right? So, and that recombination current, I will not derive that, I'll just write down. So this recombination current comes in this yeah, you means you could read in the books, but uh, uh, at this point you just know the equation. So this depends on this factor, right? So when you derive this equation, so this recombination uh, current is, so if see recombination current depends on e to the q applied voltage by 2 kT, right? So this is nothing but how many electrons and holes are traveling across the junction, right? Definitely, if more electrons are traveling from N to P or more holes are traveling from P to N, then your recombination will be higher, right? Also, it depends on the width of the depletion region, right? If the width of the depletion region is high, your recombination will be high, right? So because they are spending more time in the depletion region, right? And it also depends on the tau. Tau is the recombination lifetime, and tau depends on the defects, right? If your junction is more defective, that means your tau will be lower. If tau will be lower, your recombination current will be high, right? So this tau is related to defects, right? Okay. So this is your recombination current, right? So you see, interestingly, the recombination current is also has a dependence on applied voltage, exponential dependence on applied voltage, but the slope is different, right? Slope is 1/2, not 1, right? And so if I actually plot, so in the log plot, so there is a recombination current always present, right? So you have a recombination current present, and this is your actual diode current, right? Let's say this is my actually diode current, and there is this recombination current. And the diode current also has, if you have very high, then also it has a different slope, right? Where this is high level injection case, right? So if you add this, I mean, basically, if you add these three components, right? So add this recombination current and diode current, you see the recombination current is only dominant. If I add it, it will have something like this, right? So your diode current will look like this, right? So basically, this will have like this, right? You see, this diode recombination current is dominant at a very low applied voltage, because low applied voltage, um, your diode current is anyway low, so recombination current will dominant because your diode current is something like this, right? Diode current is below, your diode current is below recombination current, right? Because diode current is increasing, because applied voltage is very low, so diode current is slowly increasing. So that time recombination current is dominant, right? So here, if you see, uh, here I have a slope of 1. This has a slope of 0.5 again, because high level injection current 1/2, and this has a slope of 0.5. So if actually, if you want to write a single equation, right? So but everything this we saw that this is dependent on Q applied voltage by KT, right? For recombination part, let's say recombination part, I have here 2. For diode current, uh, this is e to the power q via by kt, and for high level injection I'll have again e to the cube here by 2 kt, right? So this is high level injection, let's say high level injection, right? So if I want to I want to have a single equation, right? So single equation will be, so how the single equation look like? Single equation will be e to the power q vf by nkt, right? So people write this, right? Nkt, n we call the ideality factor, right? Here n is the ideality factor. So this is the modeling part, right? But actually, if you look at the diode characteristic, you have 3 different regions recombination. And please keep in mind, if a diode is defective, right? As I told you, right? Your junction is defective, then your recombination current will be high. So you will see, you will have this kind of characteristic, right? And if you want to check whether your junction has a lot of defects or not, just look at the lower applied voltage part, right? So this with defects, um, if you have not done a very good fabrication job, right? So then your diode will be defective, and you will see a lot of recombination current, right? Right. But for ideal case, right? Ideal case, I don't want any recombination current, right? So for ideal case, my n will be 1. So n equal to 1 for an ideal diode. For an ideal diode, n is 1. But for a practical diode, right? So this n will not be 1. N will be somewhere between 1 and 2, right? Because I am varying from 0.5. So here 2, you see, here I have 2, here I have 1, here I have 2. So this will vary between n equal to 1 to 2. For the, so for the silicon case, we actually observed this recombination part. That's the reason we tell the ideal factor for silicon will be somewhere between 1 and 2, right? And somebody told, okay, let's put it as 1.5, right? See, that's why I read in the books, right? Your diode current is Q up via by NKT and is equal to 1.5 for silicon, right? But for a germanium case, let's say if I think for the germanium has a very high Ni. Ni means so your diode current is very high, right? For germanium, your diode current is very high, right? Because Ni of germanium is 1,000 times Ni of silicon. That means at same and and your current is proportional to Ni square, right? That means at the same applied voltage, your current in germanium is 10 to the power 6 times current in silicon if the dopings are same, right? So in germanium, your diode current is so high that your recombination current is not seen. Even if there is recombination current, you don't see it, right? You have recombination current, but your diode current overrides the recombination current, right? Even you go to very low applied voltage, your germanium case you will not see the diode current, right? Sorry, recombination current, right? That's the reason people tell, okay, germanium diodes are more ideal than silicon diode. So ideality factor for germanium n equal to 1, right, for germanium. But if you go to gallium arsenide, right, it has Ni, means Ni very low Ni because 10 to the 7. So it is again, your current will be 10 to the 6 times low. So there also you'll see the recombination current. Your ideality factor will be even higher than means silicon, right? So the ideality factor is a modeling concept. So you should not really, I mean, as a device engineer, we don't really consider the ideality factor. We have to draw this characteristic in the 3 different regions. And even if you go to the lab and measure a diode, you will see those 3 different regions very clearly. Okay, so this is all about the ideality factor. Anyway, any questions here? Swati, Om, Nishant, Monica?
No, sir.
All right.
No, sir.
No, sir.
Okay. Okay, so yeah, so this is done. Another thing I have to tell you. So when I'm talking about this reverse saturation current, so let me. So this part needs to be very clear also because we'll also deal with reverse saturation current later. So this is P side, this is N side, and I have my depletion region. Okay, right? So in the reverse saturation means basically here in the reverse mode, basically I am my applied voltage is positive. I mean, in this case, right? So I am reverse bias case, right? Uh, but see when you are reverse biasing this junction, in this case, when your applied voltage is positive voltage you're applying to the N side, right? So there is no electron injection, right? So electron injection here and hole injection here is very low, right? This is very low, right? Very low means even a non-existent because as I told you, right? So your Fermi, I mean your Fermi function is exponential, right? So little bit change in reverse bias means it will reduce the electron injection exponentially, right? So when you go to negative applied voltage or reverse biasing, that means it is reducing the injection from N to P or hole injection from P to N exponentially, right? And so this diffusion current is non-existent, right? So in the reverse bias your diffusion current, because forward bias you are mostly dealing with the diffusion current, right? Because electrons are injected then they diffuse, right? So diffusion current is not there, right? But there is some current, right? Because we mentioned, right, there is some current, right, which is here I mentioned, right, q ni square dn by nln or q ni square dp by ndlp, or we have this current, right, reverse, right? So this current, right, let me copy this here. So this this current here is because of minority carriers, because you have an electric field, you have a electric field here, right? Because and this electric field is very large, right? Because in the reverse bias your electric field is very large, because your electric field depends on the applied voltage across the junction, and the reverse bias your field is also large, because your depletion means your we could see that, we'll see that later, your field is large, right? And here you see there are holes and electrons this side, and I have minority carrier electrons, so electrons are here, right? And I have also minority holes here, right? So this reverse saturation, reverse current is nothing but the injection of this minority carriers, right? So when I talk about forward bias, we have injection of majority carriers, right? Because electrons are injected from N to P and holes are injected from P to N. But in the reverse bias, your minority carriers, because you don't have majority carrier injection, there is no injection, right? So the minority carriers, because electrons, so electrons are moving randomly in the P side, the moment they come across this junction or this edge of the depletion region, they experience this field and they just flow, right? So electron go. So because electrons are randomly moving inside the P region, right? The moment, let's say by moving, they if they come across this across this depletion region, right? So near to that, then they experience this field and they're just pulled, right? So basically, and this is the whole, right? So basically, you see the reverse bias current is because of the minority carriers, and the current is because of drift, because this minority carrier current are pulled to the from P to N side, actually electrons going from P to N side and holes are going from N to P. And this hole here, I'm talking about Ni square by Nd time of hole here, and you have Ni square by Na time of electron. That's the reason I have this Ni square by Na here, right? Because in the reverse saturation current, right? So Ni, because, and we could also derive, because I have Ni square by Na electrons, and they are experiencing this field E, then how much current I'll have, right? You'll get the similar equation, right? Please keep in mind, in the reverse bias, the current is because of drift, and mostly because of the minority carriers, right? Minority carriers going across the junction, right? Okay. All right. So this part is also clear, I assume. Okay. So now I'll go to the next part. It's also an important part, because because in most of the case we'll deal with narrow base diodes. So earlier till now we were talking about wide base diodes, right? So wide base diodes means I'm talking about the width of these regions, width of this P type and N type regions are higher than your diffusion length, right? So WP in the wide base diodes, earlier also we discussed, so WP is more than Ln, right? So much higher than Ln, right? So the electrons are injected, then they recombine inside the P region also, right? So similarly, holes are injected from P to N, but all the holes are recombined inside N region, right? So they those things we call wide base diode. But in many applications, in most of the applications, we deal with narrow base diodes. So narrow base diodes, we have diodes where your WP and WN, WP is less than Ln and WN is less than LP. That means these electrons are injected. Let's say I have electrons are injected, but these electrons do not recombine. All those electrons are not recombining inside P. That means electrons are reaching the metal junction here, right? The electrons are reaching the terminals, right? The metal part, right? So, so basically, what happens is another thing. Will also because boundary conditions, because these are the boundary conditions, right? So I know that how much electron I have at x minus xp. But in the previous case, in the wide base diode case, I told, okay, at in minus infinite, your number of electrons is zero. The excess carriers is zero, because most of these excess carriers are recombined inside P. But here that is not happening. That means my base is so narrow, my p region is so narrow that the electrons are not recombining, right? So your wp is less than ln, so electrons are also reaching this metal junction, right? So this metal semiconductor contact, so interestingly, this metal semiconductor contact has a lot of defects, right? So because see, if you have a semiconductor, right, let's say this is p type, and I am depositing metal on top of it, right? So we have also discussed the crystal structure, right? So in a semiconductor we have a lot of dangling bonds, right? I have a lot of dangling bonds because each silicon has to, means each silicon covalently is bonded with four different silicon atoms, right? But since I'm cutting the wafer, right, we have some dangling bands, right? And when you deposit metal on top of it, some of those, so this metal, this semiconductor forms some bonds with metal, right? But not all of those bonds are filled, right? So here this is a defective part, because metal semiconductor junctions, they are more defective than semiconductor junctions, right? So what happens, that the recombination lifetime at this point, right, recombination lifetime at the metal semiconductor junction is very high, sorry, very low, right? A lot of recombination happens because I have dangling bonds and defects there. So in what is happening in narrow base diode case, right, if you look at the boundary condition, so I have electrons injected here, then the electrons diffuse, right? And some of the electrons also reach the edge of the p region, that means metal semiconductor junction, and they recombine there because there are a lot of recombination centers for the electrons to recombine, right? So so you could assume that the excess minority carriers are becoming zero here, right? Excess minority carriers are not becoming zero inside p type region, but they are becoming zero at the metal semiconductor. This is the boundary condition you have to apply for narrow base diode, right? Okay, so so with that, if you want to do the derivation, so it is exactly same. So let's say I am talking about electron injection, or let's say I'm talking about electron injection. So delta NP at minus XP, uh, I know, right? So this much electron I am injecting at this, right? Means I have this excess minority carriers at minus XP at this point here, right? This point, right? Right, and these electrons will diffuse, right? So then I have to write down, if I write down this continuity equation, so I'll have something like this, right? 1 by q uh, Jn by del x plus g minus r. But here my generation, I don't have any generation, so this part will be 0. And recombination, because I have a very narrow base, so I have very less recombination happening in the silicon, so I could also put it 0, right? So my equation is 1 by q, um, so del by del x, so this is, it should be diffusion, so this is q dn delta np x by del x, right? So this is nothing but dn del square np x by del x, right? Okay, so this is 0 because in the steady state condition this will be 0. So this is my equation. In the earlier case, I was solving this equation, right? Delta npx by tau, right? Right. So I had this tau n, right? But here there is no recombination happening, so I could remove this, right? So this equation I have to solve, and I know the equation. If I solve this equation, so your del npx will be some constant, let's say ax plus b, right? Because this is a partial differential equation, so del square npx by del x equal to 0. So the solution is ax plus b. Then you have to apply the boundary condition here to find a and b, right? And what are the boundary conditions? So boundary conditions are, so delta np, right, at x equal to xp, which is minus xp, equal to Ni square by Na e to the power q via by kt minus 1, right? Okay, so this is one boundary condition, so condition 1, right? And second condition is your at wp minus wp, right? This becomes 0. This is because of the metal, all these minority metal semiconductor junction, all those minority carriers anyway will combine, right? So if I use these two boundary condition, I could find A and B, right? So let me write down the final equation. I'll not do the derivation. I mean, you could do uh, later. So so basically my delta npx, I could write down npx is ni square by na e to the power q applied voltage by kt minus 1, and I'll have wp plus x, means this is very means you know how to solve it, right? So I have this delta npx equal to ax plus b, and you know the two boundary condition. If you put and find the a and b and just do it, so it will be in this way, right? And similarly, means your jn, you could write down, right? This is q dn del npx by del x. So if you do that, then this will be q dn ni square by na e to the power q vf by kt minus 1, right? And this will be wp, no, this will be 1 by wp minus xp, right? Okay, so so this is similarly you could find also jp. I means how much, because if holes are injected also from p to n, and you could do the same um, uh, means same boundary, you could also apply the boundary condition, and you could also find qdp ni square by nd. Please do it yourself, because I am skipping it here for the interest of time, because this is just you just have to find the solutions of the differential equation and just put the boundary condition, right? So it will not be very difficult. Wn by xn, right? So your total current, so here you see your total current will be anyway the whole current plus electron current, right? So now your so here, I means if you see this equation, this equation, this is the electron current, and this equation, and if I assume that okay, this fine, wp is smaller than lp, but I could also make one more assumption that wp is more than xp, right? So xp is the depletion within the p region, right? So let's say wp is more than xp and wn is more than xn. Then I could also little bit simplify this again, right? So I could little bit simplify. So my electron current will be q dn ni square na wp, right? um q vf by kt minus 1, and your jp, the whole current, is q dp ni square nd times wn e to the power q bf by kt minus 1. So here, so these are the equation for narrow base diodes. For narrow base diodes or narrow p and n diodes, so basically you see, if you compare, right? So here you could clearly see, right? So in the earlier equation I have lp here, right? lp and ln here. Now lp and ln are replaced by wp and wn, right? So your current now depends on the width of the p region, and the current depends on the width of the n region, right? So so we could also see when we go to bipolar transistor, you know that bipolar transistors, for npn transistor, your current depends on the width of the base region, So this is because that is a narrow base diode, right? Narrow diode, right? So 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 it will be, so basically in case of narrow diode case, so your LP and LN are replaced by WP and WN. That means your currents now depends on the width, right? So you as you go on reducing this width, your current will increase, right? So your current, your electron current. So let's say I have I have a N plus P diode. See, if I have a N plus P diode, right, and my WP is much less than Ln, right? For N plus P diode, my current is because of electron. Oh, I have only electron current, right? So my total current will be Q dn Ni square Na WP times e to the power Q Vr by Kt minus 1, right? So see here this equation. So now my current, definitely my current will depend on applied voltage, right? It's exponential dependent on applied voltage. At the same time, my current also depends on this WP here, right, uh, right. But WP is a variable, right? In the previous case, in the white base diode case, right? White base diode, your J was Q dn Ni square Na Lp, right? E to the power Q Vf Kt minus 1, right? So please think now, right? So in the white base diode, Lp is constant, and Lp is a function of doping, and that is constant. You cannot do anything with this. Lp is constant, right? So your current is only dependent on applied voltage, right? Now, in case of narrow base diode or narrow diode, your current is dependent on applied voltage as well as WP, right? So you could, even if your applied voltage is constant, you could increase current by managing your width of the P region, right? Previously, it was not possible, right? So now I have two control parameters, right? To get high current, I could change V up, I could increase applied voltage, or I could reduce WP. That is what we call the control. There is another control terminal that will come in the bipolar transistor. Bipolar transistor, your current is same, right? It's a PN junction, right? NPN. So this is a PN junction. But now I could change the current by changing the width of the base region, right? So this is coming because of this narrow base, right? So your width of the base should be much lower than Ln, right? Then you could control the current not only by applied voltage, you could control it by changing the width of the base or width of the. So that's why it's called narrow base diode, because people started thinking about bipolar transistor by where they control the base width to control the current. So that's why I call the narrow base diode, right? So just keep in mind, if your WP is less than Ln, then your current depends on applied voltage as well as width of the P region, right? So you have two control terminal, two control terminal. You could change the current by changing the applied voltage. You could change the current by changing the WP. Okay, so this is narrow base diodes. I think we have covered this part, and we'll emphasize this part again when we go to bipolar transistor, right? So we have almost derived the current equation. We don't now understand how the current flow in PN junction, what are different components of that current. And now we'll go to in the next class, I'll just discuss about breakdown voltage, like avalanche breakdown, Zener breakdown, and those concepts. Then we'll go to bipolar transistor, bipolar junction transistors, right? Okay. So I'll not do anything more today. If you have any